Yeah, so I want to start my talk with thanking the organizers for inviting me and giving me the opportunity to present my joint work with Andrei Lysov on this beautiful workshop. So today I'm going to talk about tropical mirror symmetry via topological quantum mechanics on trees. So most of the results are kind of published in these two long papers. So it's like 80 pages each. So today I'm going to give like quick overview, like trying to give as less technical details as possible without losing the general idea. Okay, so the plan of my talk is the following. So I will start with a notion of Landau-Ginzburg-Saito theory and a notion of tropical Gromov-Witten invariance. So basically, tropical mirror symmetry is a relation between the two. And the key ingredient to prove the tropical mirror symmetry is to use higher topological quantum mechanics on trees. So that will be our main tool to establish a relation between Gromov-Witten theory, tropical Gromov-Witten theory, and Landau-Ginzburg-Saito theory. Okay, so let us start with Landau-Ginzburg-Saito theory. So some of you, especially if you come from physics background, might be familiar with this famous three-point function. So here we are looking at one-dimensional Landau-Ginzburg theory. So phi1, phi2, and phi3 are just three holomorphic functions, and W is one-dimensional holomorphic superpotential. And the three-point function is given by this nice residue formula. So let us notice two important features about this formula. So first of all, the correlation function is invariant under interchange of phi1, phi2, and phi3. So it is symmetric in all three arguments. So the second feature, which is less obvious, but still is very useful nevertheless, is that if I shift my holomorphic function phi by something proportional to W prime, so V is another holomorphic function. So then the residue doesn't change because the W prime in the numerator will cancel W prime in denominator, and therefore we'll get like the same residue expression for phi and phi plus VW prime. So hence we can say that this three-point function is well defined on a Jacobi ring, which is quotient of the holomorphic functions of x by the ideal generated by derivatives of W. So for one-dimensional W is just ideal generated by W prime. Yes? So everything is one-dimensional. So phi is function on one-dimensional complex manifold. W is function of one-dimensional complex manifold. So no, phi depends only one holomorphic variable z. So there is one holomorphic coordinate, but any W function also on z. So phi and W are just holomorphic function of one variable. So that is like just for simplicity. So we will see in a few slides how to generalize this formula to higher dimensional case. Okay, so now given a success of writing down a very simple three-point function of Landau-Ginzburg theory, we can ask a natural question: can we go to higher point functions? Can we write down a similar residue type four-point function expression? Okay, so let us try to recall the definition of four-point function. So the definition from QFT is the following. So we take like three observables, phi1, phi2, and phi3, inserted at some point z1, z2, z3 on a source. And then we have a fourth observable, which we need to integrate over our S2 source. So first we need to take path integral over our fields, and then we need to take this integral over S2. So that is a formal definition of a four-point function. So the key observation is that this kind of observable phi42, which is some descendant observable constructed from holomorphic function phi4, it actually has a very similar structure to the superpotential dependence of this action. So efficiently, if we shift our superpotential by epsilon phi4 and expand to linear order in epsilon, we will precisely get this integral over S2 phi 4 second descendant term. So that observation gives us an immediate conjecture for a possible 4-point function. So we just take our 3-point function, which is defined for any w, and then we deform w by epsilon phi 4 and kind of look at the linear term in epsilon expansion. So given the simplicity of this 3-point function for one-dimensional theory, so we can immediately substitute and take a derivative and get this residue type formula. So now in denominator we have w prime squared, in the numerator phi 1, phi 2, phi 3, and phi 4 squared. Okay, so is that all? Apparently not. So if you look at kind of our formula for a 4-point function, you can immediately notice that it is manifestly symmetric in first 3 arguments, phi 1, phi 2, phi 3, but not quite symmetric in phi 4, because phi 4 comes with a derivative. And another problem with this 4-point function is that if we shift, say, phi 3 by something proportional to w prime, or for simplicity, we can choose phi 3 to be in this ideal generated by gradient of w, like phi 3 equal to w prime. So we expect that the answer should be 0 for this 4-point function. That 4-point function should be invariant under this supersymmetry transformations. So let us substitute in our expression for a 4-point function w prime instead of phi 3. So then we will have a cancellation of w prime in the numerator and denominator. And the resulting expression will be just a familiar 3-point function for phi 1, phi 2, and phi 4 prime. So therefore, there is no way to make this expression vanish unless you ask all 3-point functions to vanish. So that are two problems with our kind of naive formula for a 4-point function. So it is not symmetric in 4 arguments, and it is not invariant under shifting of phi's by element from a gradient ideal. So can we resolve these puzzles? And the answer is yes. And in order to do this, let us draw one more intuition from, I don't know, physics, QFT strings. So in this original defining expression, when we have integral over S2, we already have like 3 other observables inserted in some points on S2. So therefore, when we integrate in this 4th observable over sphere, we have some kind of suspicious regions where this observable, the 4th observable, come close to insertion points Z1, Z2, and Z3. So therefore, it is natural to kind of conjecture that something interesting might be happening at these points. That we take our original expression when we just deform w by phi 4 and try to add 3 more terms corresponding to the situation that phi 4 close to phi 1, phi 2, and phi 3. And the natural notion of these terms are contact terms because they emerge when phi 1 touches, phi 4 touches some other observables. So in order to kind of fix the first problem about invariance under shifting by w prime something, so we can choose our contact term in this form. So we take a product of 2 fields phi 1 and phi 2, and then we subtract from this product the following element. So given a product, we can compute its class in Jacobi ring. So we can just project on classes in this quotient space. But then we also introduce a new object S, which we call a section. So it is a map that goes from a Jacobi ring to holomorphic function. So it inverts this projection pi w. So this section does not exist canonically. Projection exists canonically, and section requires to make a certain choice. However, in order to solve a first problem about invariance by shifting by w prime something, it is sufficient to take any section. So if you look at this expression when one of the phi's is w prime, so then projection just vanishes, and we can divide through by w prime and just get a derivative of the other field. And that will give us precisely a 3-point function with, say, phi1, phi2, and say phi3 prime. And that precisely was this extra non-zero term that we got when we tried to check supersymmetry invariance for our naive formula. So it's kind of any choice of a section solves a problem about supersymmetry invariance. However, if we want to restore symmetry in all 4 arguments, then we need to make a very particular choice of this section SW. And apparently, for some different applications, a similar problem was studied by Kyoji in 1983. And since that time, this section has the name Kyoji-Saito's good section. So sometimes for short, I will just say good section or Kyoji-Saito's section. So you can show that if we choose this Kyoji-Saito's good section, then this amplitude is indeed, this 4-point function is indeed symmetric in 4 arguments. Okay, so given success with a 4-point function, we can generalize this idea to a higher point functions, which we can define in recursive way. So for a 3-point function, like in a generic Landau-Ginzburg-Saito theory, so Saito stands for this additional data of a good section. So the 3-point function is still given by higher dimensional residue formula, which here, for simplicity, I wrote as a sum over critical points, assuming that they are isolated. So then for higher point functions, we do a similar procedure that we did for a 4-point function. So for n plus 1 point function, it is a derivative of n point function with deformed superpotential plus n contact terms where phi n plus 1 touches with one of the phis. Yes. Second descent? No. For a 3-point function, not need to insert second descent. Because of SL2C action. Like SL2C action, it efficiently it allows you to kind of fix a position of 3 points to say 0, 1, and infinity, but fourth point, it kind of remains 3 point. Or equivalently, you can say the dimension of a moduli space M03 is 0-dimensional, just a point, but M04 is 1-dimensional. And this integration is integration of a 1-dimensional moduli space. And the moduli space of market points on a sphere. No, we are looking at kind of, okay, we are looking at correlation functions in Landau-Ginzburg theory. So we need to define it for the reasons of mirror symmetry. So the mirror symmetry will be formulated in terms of this integrated, as if you want, correlation functions in Landau-Ginzburg CFT. So in our case, we are not studying this theory just for kind of curiosity, but we are studying it having in mind application for a mirror symmetry. So that will be a kind of B model site of a mirror symmetry for a toric variety. So yeah, so secondly, you can think of it as a topological string theory. Yeah. That's a good question, and I will, like, if you wait for a couple more slides, I will show you explicit expression for computing a good section for a mirror superpotential to a toric variety. So for a general double, like for polynomial of one variable, it's extremely easy to compute. It's like trivial answer. So in a case when you have polynomial superpotentials of multiple variables, so that's a problem that Kyoji decided to solve it, and it turns out that in the case of two variables, the formulas can get like quickly very complicated. But for exponential superpotentials that are mirrors, it turns out that you can write down a nice simple expression. So Yes, there is this paper by Lily Saito where they not quite computing a good section as W, but they're computing some good filtration that's known to be equivalent to a good section in a certain cases. So yes, they kind of did some computation, and for CP1, I think our result matches with them. But in their case, as you say, it is hard to compute it for some other exponential superpotential. So yeah, but that should be a part of a mirror symmetry tool. Like we should be able to have a full data on both sides to compute the invariance and to have a match. Okay, so and kind of finally, so the generalization of that formula where we divide by W prime and take a derivative is the following. So we still subtract a good section of projection of a phi. So that gives us an element from a gradient ideal, which we can write down as a vector field V, holomorphic vector field V applied to W. And then the contact term for phi is just taking holomorphic divergence, like divergence with respect to holomorphic top form of this vector field. Okay, so now let us go to our second ingredient, which is tropical Gromov-Witten theory of our tropical mirror correspondence. So the idea of tropical geometry, or like complex version of tropical or complexified tropical geometry, in kind of physicist term, is a particular scaling limit of a complex geometry when you kind of decompose your variables into radial and angular variables. So that usually requires some kind of toric structure to be present. And then what you do, you keep angular variable as they are, but rescale radial variable. And then you kind of see what you get, like if you have, say, some linear equation in axis, that will give you some interesting equations in R phi coordinates. So that is essentially our kind of physicist approach to tropical geometry. So now I need to give a bit of kind of details about toric varieties, because that will be our data for Gromov-Witten invariance on A side of a mirror. So toric variety of dimension capital L is essentially a compactification of C star to the power n by lower dimensional orbits. So the kind of radial part of C star to the n, like if n equals 2, is just two-dimensional plane, and the radial compactification is a compactification by a certain number of lines at infinity. So if we just choose like 3 lines in a form of triangle, that will be a familiar compactification of C star squared to a CP2. So in a more general case, for a CPN, you need like n plus 1 hyperplanes. So the data about hyperplanes can be characterized by a primitive integer valued normal vector. So it should be integer valued because secretly we also have some circle, some torus fibered over this radial base, and there should be some circles shrinking on compactifying hyperplanes, and these circles should have integer homology classes, and these homology classes should match with this vectors B. So that's the reason why they should be integer valued. Okay, so now tropical curves. So we have a nice description of our, say, two-dimensional toric variety as a kind of two-dimensional plane compactified by some lines at infinity. So the tropical curve is essentially a graph drawn in this two-dimensional plane with a circle fibered over it. And if it's Gino-zero curve, then it's just a tree with a circle fiber. So circle, it kind of lies inside of n-dimensional torus. That's why it carries some integer homology class, some integer vector in n-dimensional lattice. So because we want the circle to kind of shrink to 0 at compactifying hyperplanes, so the leaves, so this kind of blue lines, they should carry this integer vector equal to a primitive normal vector to the corresponding kind of compactifying divisors or compactifying hyperplanes. So then we also have vertices of this tree, And near vertex, we have like 3 circles merged together inside of n-dimensional torus. And that's only possible if they have like homology classes added up to 0. So that's why we have this vertex balance condition that these integer vectors assigned to edges should add up to 0 for each vertex. So then we want to study kind of tropicalization of holomorphic curves. So that gives us, like holomorphicity condition gives us a relation between kind of slopes of these lines in kind of radial plane and these homology classes of circles in a torus. So they should be given by the same integer vector m. So now here I kind of drawn you like 4 different tropical curves, which are degree 2 tropical curves in CP2. And you can see that they can have quite different topological shapes. So they have like a different assignments of a vectors. So blue vectors are kind of equal to these normal vectors to black lines, while green vectors can be restored by just applying balance condition for vertices. So here it's kind of clearly what are the integer vectors for green lines, for green edges, but for a red edge, it's kind of a bit harder to compute it. So that's why I computed it for you. So it's 2,1 vector and 1,2 vector for the second and third picture. So in this presentation of a tropical curve, it's kind of quite straightforward to compute what are the moduli of a tropical curve. So essentially, because all these compactifying divisors are at infinity, so we can freely move the center of mass of this curve. So that gives us one moduli for a radial motion of a center mass and one moduli for angular motion of a center mass, which together combine to c to the power n moduli. So we can also freely change the length of internal edges, like length of these green and red edges, and we can also twist the corresponding circles fibered over these edges. So that gives us one complex moduli for each internal edge. That is a product of like R plus and S1 for length and twist. Okay, and the last comment is that we want to study smooth curves. So that's why we can only have 3 valent vertices. Okay, so now given a notion of tropical curves, we can set an intersection problem, like how many tropical curves of a given degree passing through some cycle. So in this simple example, I drawn like an answer to a question of how many these blue curves, which are degree 1 tropical curves in P2, passing through like 2 points on P2, like these 2 red points, point 1 and point 2. So due to the constraints on kind of slopes of these lines, you can see that regardless of your choice of points 1 and 2, there will be exactly one blue curve with these slopes. So, and here on these 3 pictures, I kind of represented different, 3 different configurations among 6 possible configurations of this tropical curve, depending on the position of points 1 and 2. So the other 3 configurations, they just interchange of 1 and 2 points. Okay, so that gives us a kind of geometric definition of this intersection problem. And similarly to intersection problem of a complex numbers, we can rewrite it as an integral of a moduli space. So we in the previous slide kind of outlined moduli space, and apparently on this moduli space you can define evaluation maps, you can pull back our cycles to the moduli space using evaluation map, take a product of them, integrate, but now because we have an additional discrete data that is kind of coloring of our graph by these integer vectors, we also need to sum over this discrete data. And so that is a kind of analog of tropical version of Kontsevich-Manin formula for the intersection numbers or for the number of curves passing through some cycles. So now, given so the short answer is yes, but it's still work in progress. So it is possible to generalize. So we can kind of talk more about it after this non-gravitational descendant. So now we are ready to formulate our main theorem, which is tropical mirror symmetry theorem. That on one hand, that it basically states an equality. So on one hand, we have a toric variety X that is given in terms of this compactification data, like some collection of integer valued normal vectors. And then we compute a tropical Gromov-Witten invariant on this X for tropical cycles gamma 1 to gamma n. And so it is like some endpoint function that depends on these gammas and depends on this compactification data for X. So then this expression equals to another expression, which is endpoint correlation function in Landau-Ginzburg-Saito theory, where mirror superpotential is given by a sum over some holomorphic functions phi assigned to each compactifying divisor. And this holomorphic function is just simple exponential function where we take like e to the product of vector b and holomorphic coordinate y on this c star to the n, which is mirror manifold in that case. So holomorphic form is just in this y coordinates, it's just product of divisor. And in the same notation, a tropical good section is spanned by a product of this phi h alpha as long as these alphas are distinct. So you have like say n+1 compactifying divisors for CPN, and then you take just distinct products of this n+1 divisors, and then linear span of this space gives you an image of good section. So therefore, in our case, it is given in a very explicit form. Like for CP1, CP2, you can immediately compute it and use it to compute this Landau-Ginzburg Saito correlation function. Okay, so having formulated this main theorem, let me proceed to our main tool for proving this theorem. So our main tool will be higher topological quantum mechanics. So let us notice that when we draw this kind of tropical curves, they kind of have some reminiscence of some kind of scattering pictures for some particles. That say we have like 6 or like 1 particle at the center that decays into 3 green particles, and then each green particle kind of decays into 2 blue particles. So that is analogy that brought us to this idea of trying to formulate some kind of topological quantum mechanics representation for this tropical Gromov-Witten invariants. And that is kind of result of our careful analysis. So essentially, you can think of this quantum mechanics as a tropicalization of topological strings. So and basically the only data about strings that remains after our scaling limit is just this data about winding modes. So essentially we have like one type of particle for each winding number m. And the Gilbert space for our infinite collection of particles is just direct sum of Gilbert spaces labeled by this integer vector m. So our particle is supersymmetric because we really want to use this particle to represent some operations on differential forms. So that was our original moduli space integrals, was some differential forms on the moduli space. So it's not surprising that states for a single type of a particle is described by a differential form, or to be more precise, U1 invariant differential form. So it is independent on phi variable, so it depends on r, and kind of dr d phi, which is in physics literature people try to sometimes replace by fermionic variables psi r and psi phi. So for this vector space we have a natural pairing. So we check whether two vectors add up to 0, and if they do, then we assign a non-zero number that is integral over target space of omega of h sigma. Our original motivation for particles was this kind of trajectories over this tropical curve that we wanted to interpret as trajectories of this particle. So the tropical curve, because it represented tropicalization of holomorphic curve, it's kind of embedded in the form of a straight line. So that's why equations of motion for our particle is very simple, like r dot equals to constant. And this constant equals to this integer vector drawn for a particular edge. So the classical Hamiltonian for such motion is just m dot p. So it's just Hamiltonian linear momentum. So if we quantize p, that will be some linear operator acting on functions, but we want to act on differential forms, so that's why we need to promote this linear differential operator to a Lie derivative in a radial direction. So our Hamiltonian, quantum Hamiltonian, will act on this state omega m as a Lie derivative in a radial direction acting on omega, and it keeps m as it was, so it doesn't change m. So most of you familiar with this Cartan formula or Cartan magic formula that you can represent the Lie derivative as an anti-commutator of exterior derivative or de Rham differential and a substitution of a vector field. And that gives us this natural formula that our quantum Hamiltonian is anti-commutator of two differentials, like Q acting as an exterior derivative and G plus acting as a substitution of a radial vector field. So apparently there is there is no dynamics in phi direction, but there is still a kind of super partner for a phi dynamics, which is J minus, which is substitution of a very similar vector field that is M with components M, but acting in phi direction. So that's why it is natural to kind of identify these two operators as somewhat similar G plus, G minus operators, because they have similar action. And this G minus acts as a parity odd symmetry of our quantum mechanics. So it basically anti-commutes with Q, anti-commutes with G plus, commutes with the Hamiltonian. So that is kind of symmetry of some supersymmetric quantum mechanics. So now we have a new data that is, because our quantum mechanics doesn't quite live on the interval, but it lives on a certain tree. So that's why we need to assign some operation to a vertices, and the operation is just multiplication of states. Like we can think of our vertex as a multiplication of two incoming states into one outgoing state. So for two states, omega 1 and 1, omega 2 and 2, so we multiply the corresponding differential forms and add the corresponding vectors. So addition of vectors is according to our kind of conservation of winding number that we saw before when we described the tropical curve. So that is kind of another kind of consequence of that property. So in our papers, we provided a kind of a more general formal definition for this HTQM, higher topological quantum mechanics on trees, like in the form of choosing this data, like vector space, differential Q, pair of differentials G plus minus, pairing G, multiplication mu2, and formulated some consistency conditions that allows us to do a certain manipulation with this HTQM. And our HTQM emerging in a mirror symmetry is just a particular example of this general construction. Okay, so now given this HTQM, we want to use it to construct some numbers, because that's our original goal, is to compute this number of curves passing through some cycles, and we want to use HTQM to represent these numbers as some kind of amplitude. But because our HTQM on a graph, I need to kind of give you more details of how to compute numbers from so-called scattering diagrams in this HTQM. So essentially, like, let us look at one of the contributions for kind of tropical curve passing, like this blue tropical curve in CP2 with divisors by 1, by 2, and by 3, passing through some cycles in red, this gamma 1 and gamma 2. So we take this picture from a tropical geometry and we construct the corresponding kind of scattering diagram for our quantum mechanics. So we replace the data about toric variety, like compactifying divisors, as a kind of states assigned to the leaves of this tree. So then the data about cycles through which this curve passes, it became insertion of some operators in some 2-valent vertices on this diagram. And then the remaining 3-valent vertex, it will kind of be assigned a multiplication. So essentially, scattering diagram is a tree that is kind of decorated by some operator states, and there also will be a propagator that emerge as an integration over this moduli T1 and T2 for internal edges. Okay, so let us kind of quickly go over this data. So leaves carry these divisor states that have this simple form, one for differential form and this primitive normal vector B for the corresponding winding vector. So then marked points carry these evaluation operators that act as a multiplication by gamma without changing winding number. And this kind of integral over this moduli of internal edges can be realized as an action of a certain propagator. So it's just a linear operator in our quantum mechanics, which for many historical reasons we call Kj minus, because in quantum mechanics mostly we don't have extra symmetry, so propagator is usually defined without this G minus part. So we try to follow standard convention. So therefore, in order to get a number from this graph, what we need to do, we need to take a divisor state B2, act on it with operator O gamma 2, act with the propagator, then do the same for this other kind of other edge. So we do like Kg minus O gamma 1 psi B1, and then we apply multiplication by B3, and then we apply a pairing for these states. So that is a way to get a number from this scattering diagram. Okay, so given all this preparation, we just one step away from formulating tropical Gromov-Witten invariance in terms of HTQM. So bear with me for one more slide. So the advantage of using this HTQM lies in the following property. So secretly, HTQM knows something about topological string, that it was secretly limit of topological string, and that's why it carries an important property that is some resemblance of state operator correspondence. So in quantum mechanics on graphs, so we can immediately assign an operator for a state. And this operator is just multiplication by a state. So in our case, we also have an operator O gamma, which is evaluation operator, that acts in a very simple way. So it just multiplies omega by gamma. And we can also realize an action of this operator as a multiplication by some state psi gamma that has the simple form gamma comma 0. So the key observation is that if we turn our evaluation observables into states, that these states are very nice states, so they are like supersymmetric states, so they are closed under G plus minus and Q, given that our kind of differential forms gamma are closed forms, but they are, in the case of intersection problem, they are Poincare dual of some cycles, so they are, by definition, are closed forms. So now, given this property, that we can freely kind of turn operators into states and vice versa, we can perform a mutation on HTQM diagrams without changing numerical value of a diagram. So we have a kind of numerical value computed for this decoration. So then we kind of turn red operators into red states, and then we will get exactly the same numerical value if we compute amplitude in this like gamma 2 representation. And we can, in principle, take a one step further to turn these black states into black operators. So that gives us some kind of interesting duality. Like here we have scattered these divisor states that was compactification data for our toric variety, while all were our like observables. But after this double mutation, we have a completely opposite picture. So now we scatter states kind of associated to our cycles, somewhat in the background of compactification data. However, it turns out that still this single mutation picture seems to be the most convenient to have like a shorter formulas for various expressions. So we will kind of turn all operators into states and just work in quantum mechanics where we have some states, propagators, and multiplication. So no operators. Okay, so final slide before the formulation of HTQM tropical invariance as HTQM amplitude. So given a state that is Q and G minus closed, so let us multiply it by some parameter, formal parameter epsilon, such that epsilon psi is even state. So then we can use this closed even state to construct a one parameter family of deformations for our HTQM. So we keep all HTQM data except differential Q the same, and for differential Q we deform it in this simple way as a G minus commutator with an operator multiplication by epsilon psi. So that is kind of linearized deformation in epsilon. So then we can express a propagator in deformed theory as this kind of perturbation theory in quantum mechanics. So essentially this brown line, which is propagator in deformed theory, is given by this infinite sum of these blue lines with epsilon psi insertions. And similarly, if you have some state V that was also some nice state like Q and G minus closed, so we can kind of deform it to another state V epsilon that is Q epsilon closed and still G minus closed. And the deformation is given by a kind of very similar sum of diagrams that we insert epsilon psi and add propagator for all internal edges. Okay, so now one final ingredient is the following. So given this collection of states psi, we can define a correlation function for HTQM states. So we take like a sum over amplitudes, like sum over possible trees, gamma, with n leaves, and then we kind of color this n leaves by state psi1, psi n, and sum over all possible permutations of this coloring, and divide by kind of dimension of automorphism group of this graph gamma. So that is might be not familiar expression for some people from a physics background, but you can clearly get the idea from this simple example that in the case of 4-point function, so like you will have like 24 terms in this summation of permutations, but each of the 4-valent tree will have a symmetry factor of 8. So that's why among 24 terms, you only have 24 divided by 8, 3 terms, which you can recognize as STU contributions to a 4-point function. So 4-point correlation function is just sum of these 3 terms corresponding to 3 diagrams. So now, given this definition, we are ready to give HTQM formulation for a tropical Gromov-Fit invariant. That here we have this our cycles gamma, tropical toric variety X, and we kind of ask about tropical curves of degree D passing through these cycles. Then this number can be computed as HTQM correlation function, where we have this evaluation states psi, which we dualized from evaluation operators. And then we need to insert a certain number of divisor states, and this number depends on a dimension B of our curve. So curve of a given dimension, it has a certain number of leaves of a given type that can be like computed from D and from compactifying divisors. Okay, so now given this representation for HTQM amplitudes, we can Yeah, black size, you can think of black size as a background. Yes. So the left-hand side depends on x. So you have like intersection in some toric variety x. So this background psi, it kind of carries information where your cycles intersect. Okay, so one of the kind of key ingredients for all mirror constructions is some secret t-duality or some secret resummation or turning of some integer valued vector into a new coordinate, into a new periodic coordinate. So in our case, we can take our states that are labeled by these integer vectors, multiply them by e to the IMY exponent as sum over all possible vectors to get a state psi that now depends on y and depends on these differential forms omega m. So one of the key property is that the multiplication for this state psi, it kind of takes very local form, so it is just point-wise multiplication in all variables like r, y, and psi r, psi phi. So then we can construct like universal compactifying divisor, which will be mirror superpotential, where we take a formal sum of all possible types of compactifying states multiplied by a corresponding generating parameter qb. So this w depends on y and depends on q's, but I kind of omit this dependence. So then we use this universal divisor state to deform our theory in kind of according to this proposition. So we, instead of epsilon psi, we use our kind of w of x that is sum of states, of even states of this form. So then, given this deformation of q, we can perform a resummation of amplitudes that here, when we sum over all possible insertion numbers for this divisor states psi, organize it into kind of universal divisor wx. So summation over k from 0 to infinity gives us endpoint function in a deformed theory, so the theory deformed by this superpotential w, but we also need to deform states like in a way according to this proposition. And we kind of denote these deformed states as a mirror states. So now, given this kind of pair of relation, that first we turned tropical Gromov-Witten invariance into this HTQM amplitudes, and then we kind of multiplied this expression by QB, by Q to the some powers and sum it over all possible Ds. So we got an expression that kind of resembles our expression in Landau-Ginzburg-Saito theory, that it is some n-point correlation function where a number of points is a number of cycles in kind of Gromov-Witten theory. So now we need to do one more final step. So we need to turn this expression that is correlation function in some deformed HTQM into familiar recursive formula for Landau-Ginzburg-Saito theory and compute a good section somewhere in a process. So that is the last part of my talk. Okay, so the key observation to kind of transform our endpoint correlation function deformed theory is a recursion relation in HTQM that is similar in nature to recursion relation in Landau-Ginzburg-Saito theory. So if I have kind of HTQM with n black states and one red state that is also Q and G minus closed, so then such n plus 1 point function can be represented as kind of linear term in a deformation of this endpoint function of this Brown states. So the deformation of Q is a familiar deformation by even state epsilon psi naught. So for simplicity, okay, in our mirror situation, all states will be automatically even states, so epsilon will always be even parameter. But then there will be additional deformation of state according to kind of similar rules as we saw before for deformation of HTQM, to kind of keep them Q epsilon closed. And now, if in this formula I can kind of write down separately a derivative of correlation function of undeformed states in a deformed theory, and separately write down a kind of contribution from a state deformation, I will get a formula with the same structure as Landau-Ginzburg-Saito recursion. That is deformation of n-point correlation function, derivative of n-point correlation function deformed theory plus n contact terms. So that is kind of below you see a graphical representation of a simplest case of this relation. That's that is abstract HQM. So that was proven for abstract HQM. Abstract HQM. So it can be A side, B side. Oh, this recursion relation, theorem 4.1. That for any HQM, you have this relation. And then you can use it on A side, B side, any HQM you want. Any closed state. As long as it's Q in G minus closed, then you have this relation. So that's just universal relation. That is basically a property of trees that you can kind of, if you have n-valent tree, then you can construct, the tree with n leaves, you can construct tree with n plus 1 leaves by literally attaching leaf to any edge of your original tree. And attaching it to attaching it to leaves gives you a deformation of state, and attaching it to some internal edges gives you a deformation of your propagator. So that is just a topological property of having this correlation function as sum of the trees. Okay, so one last step. So we kind of get this recursion, Landau-Ginzburg-Saito type recursion relation in HTQM. So now the final step is to get holomorphic functions, because in Landau-Ginzburg-Saito we have only functions of y and not states in some abstract HTQM. So then we need to find a way how to turn these mirror states from HTQM into holomorphic functions. So we call these holomorphic functions y-gems. And that is kind of complicated technical part, so that's why I will kind of use CP1 example to explain it. So in CP1 case, mirror superpotential is just this simple formula. So then the corresponding mirror state is just our original kind of delta function observable that is dressed by two kind of tails. So we are in one dimension, so we have tail going to the left and tail going to the right. So formally from this expression, you have like a free parameter R0, which is a point where your observable is inserted on target. So that is like point on target through which path. So formally you can take a limit R0 goes to minus infinity to eliminate one of the theta functions and eliminate delta function like the pointwise limit. And then what you will get like precisely this coefficient in front of a theta function that is constant if your R0 goes to minus infinity. You can do it more carefully to kind of formulate this change in R0 as a kind of an addition of Q-exact term. So adding a Q-exact term for this state chi plus will turn your mirror state, that is this complicated expression, into simple holomorphic function of y q plus e to the y. So that is compactifying dividers. Like for CP1 is a C star compactified by 2 points. And these 2 points, they kind of have a normal vectors pointing like to the middle. So it's plus 1 and minus 1. So one-dimensional vectors. Okay. Okay, so final technical slide. So the outline of our kind of bridge to Landau-Ginzburg theory is the following. So we start with this n plus 1 point amplitude. So we shift psi by Q-exact term. we turn it into holomorphic function, so that doesn't change endpoint correlation function. And then we apply a recursion formula for this phi n plus 1. So the deformation of HTQM gives us a deformation of superpotential, and deformation of state is precisely a deformation by a tropical contact term, and the corresponding tropical good section is precisely given by a linear span of y germs of a mirror states for all the RAM classes of X. And that is equivalent formula to what I shown before. So I think, yeah, I can have 1 minute for summary. Okay, so the summary or take-home lesson from my talk is the following. So this new notion, Landau-Ginzburg-Saito theory, is essentially some kind of refinement of Landau-Ginzburg theory by adding an additional data that is Kyoji-Saito good section. That allows us to define amplitudes in this theory kind of recursively using Saito's good section. So tropical Gromov-Witten invariance is essentially some special scaling limit, epsilon goes to 0, also known as tropicalization, of ordinary complex Gromov-Witten invariance. Moreover, in some cases, people manage to prove tropical correspondence theorem that this scaling limit doesn't give rise to any loss of information, that Gromov-Witten invariance over complex numbers are identical to Gromov-Witten invariance in a tropical setting. So then higher topological quantum mechanics is essentially a tropicalization of topological string where you have like many types of particles labeled by windings. So mirror superpotential in our construction emerges as a deformation of HTQM by these divisor states. So they are states that carry information about your target toric variety X. So mirror Landau-Ginzburg theory emerges as a localization of HTQM to Y germs, and similarly, tropical good section is a localization of Y germs to mirror states. And in my almost final slide, I want to advertise a little bit Strings conference that will happen next year in Shanghai, so with Strings 2026, and I am, as one of the organizers, welcome all you to come and visit Shanghai. So that is right before the ICBS. So you can come to Shanghai to attend Strings and then take a fast train, go to Beijing and attend ICBS 2026. Thank you.
Do we have questions?
Okay.
Okay, so given that on the A side you got tropical limit of the A model, which is this quantum mechanics on the graph. On the B side, I would expect the tropical limit of the B model, but the theory that you described doesn't. It looks like some kind of something different.
No, so the story is that because you have tropical correspondence theorem, then taking epsilon goes to 0 limit doesn't change Gromov-Witten invariance. So you are taking the limit, and that provides you not a different invariance like tropical, but a different description of the same Gromov-Witten invariance of a complex number. So just different presentation. And that's why in the mirror symmetry, you have precisely the same Hori-Waffa mirror superpotential. So our Wx is identical to Hori-Waffa expression. So the only additional bit that we can get by tropicalization is this Kyoji-Saito's good section and an explicit way of constructing mirror on the level of correlation functions without this extra construction of change of variables that was mentioned by Mauricio in his talks, that usually mirror involves some complicated change of variables from A model to B model. But in our case, good section kind of plays the role of a data that knows that secretly knows this information about complicated change of variables, and that's why on the B model side you don't see anything fancy. It's like old good B model, like in as an usual setting.
Two questions. One is, everything you did here is kind of genus zeros.
Genus 0, no gravitational descendants. Yes.
Is there any way to extend it?
So gravitational, extending to gravitational descent, as I say, is a kind of rather straightforward. So it is essentially like inserting operators not in the two valent vertices, but in the higher valent vertices. So that kind of keeps you still, your graphs are still trees. So in a tropical setting, people manage to describe higher genus Gromov-Fit invariance on P1 by studying like graphs instead of trees. However, in that situation, there is this kind of complication about some multiplicity factors, like Mihalkin's multiplicity factors in the case of genus bigger than 0. So in our case, we hope that our formula for a moduli space integral can be somehow once again carried into some quantum mechanical presentation. But that is kind of our hope, and we are still far away from having even some simple examples of that. But kind of hope is that the program will carry through. So at least on a kind of Landau-Ginzburg side, so that is something that is a bit easier. So I managed to, like, in the case of CP1, there are like many explicit formulas for Gromov-Fit invariance with descendants at higher genus on CP1. So that was computed by different methods like Okounkov-Padharipande, some Dubrovin, Young, and some other people. So I managed to kind of reproduce some of the higher genus correlation functions, like using some correlation functions in Landau-Ginzburg Saito theory at genus 1 and genus 2. But it still was more or less like ad hoc construction, and I still don't have like a tropical realization of that construction. But that gives me some hope that at least on a B model side, I can capture at least this invariance numerically. So maybe I can find a tropical realization for a map between observables on A side and observables on a B side.
My second question was, is there any kind of open string version? I don't know, I'm using words that I don't know what in physics, but I'm asking, is there some equivalence of categories? Is there a category specifically between some category of matrix factorizations on the B side and something you could construct from the tropical geometry?
That is an excellent question. It's actually like two questions in one. So the question about open Gromov-Fit invariance. So when you have like counting some curves that end on some Lagrangian submanifolds, so that is kind of easier question than this homological mirror symmetry that is. So in that situation, so we kind of have some partial results of some simple open Gromov-Fit invariance, like in tropical setting. But still we are far away from a mirror formulation. So there is like a conjectured mirror in this situation given by also in the papers of Hori and Waffa as some kind of period integrals where the cycle depends on the type of Lagrangian submanifold that you take. So that is a question that I at least understand and I can approach. So for homological mirror symmetry, I'm still kind of in the process of learning it, like learning it from Mauricio Romo and some other great people in CIMIS. So that's why for this question, I kind of don't have like good idea whether it's possible, whether it's hard. So for that question, sorry, I have no answer.
Other questions?
In the usual mirror symmetry, Taylor moduli is exchanged with the complex structure. It's something similar.
So you see, like in a usual mirror setting, you have like a pair of Calabi-Yaos. So in our case, our mirror, on one hand, it is easier, but from point of view of Calabi-Yau, it is a generalized mirror symmetry. So instead of having complex structure deformations on a B side by Beltrami differentials, we have generalized complex structure deformation. So you can think of complex structures as defined by some deformation of Dalbo operator. So you can deform your Dalbo operator by Beltrami differential. So that's what happens in ordinary mirror. But in generalized mirror symmetry, you can describe Dalbo operator by the following operator. So W is holomorphic function, so dW is holomorphic one form, and this thing is a deformation Dalbo operator. So it still squares to 0, and if I set W0, I return to original Dalbo operator. So in our setting, mirror superpotential is a generalized complex deformation. And kind of Keller moduli on A side, like this kind of QAs that were like these parameters in that were corresponding to these compactifying divisors BAs. So they precisely became coefficients in a mirror superpotential. So in this sense, the scalar moduli from A side turn into coefficients of W, and W plays a role as generalized deformation of complex structure in that sense.
Thank you.
Other questions? If no, then let's send the speaker again.